Welcome to the Beyond Tech podcast, a podcast designed for engineers. We aim to demystify technologies around safety and give you a lot of information so that you can make an informed decision when designing a safety system.
We cut through the fluff and we avoid those typical statements like robust and reliable, and we look at the real world challenges rather than just quoting off the data sheets that often just look at the best case scenarios.
Each episode will take on one gas or flame detection technology and break it down. How does it work, when and where to use it, and the potential drawbacks, as well as looking at maintenance requirements.
In this episode, we take a look at the catalytic bead sensor, also known as the Pellister. Once the workhorse of the flammable gas detection market until the invent of the infrared technology in the 90s. There's no better person to introduce the catalytic sensor than Marcus Oertel. Welcome, Marcus.
Yes, welcome. Marcus has been with Dräger for over 25 years, with the last 13 of them being spent as a product manager for our sensors. He's also on the German committee, and this is in letters. I'm not going to try and butcher the German explanation, but maybe you can explain it later. DKEMEWAGG, which is the explosion protection for gas detection equipment. So, welcome, Marcus. Are you ready for a little icebreaker?
So we ask this and that. So we give you two options. And it's your best and quickest answer. So the first one, are you an early bird or a night owl?
So I would say, first of all, thank you for the invitation. And about your first question, nowadays I'm an early bird, yeah?
I bet you are as well, Graham. Coffee or tea?
Black coffee.
Nice.
Cats or dogs?
I like both, but we have at home a cat, so.
Lovely. Pizza or burger?
Burger.
And for holiday, a city break or country escape?
Country escape.
Nice.
Perfect. So, now that we got that little bit of fun out of the way, let's dive in a little bit deeper into catalytic bead. So, Marcus, please tell us, how does catalytic bead actually work?
Yeah. We use the effect or the property, so we want to detect flammable gases, so they are flammable. So this is a property we use to detect it. So it's very simple. We have a wire, a platinum wire, arranged as a coil, which is heated up at about 400 degrees, and it's coated with some catalytic material to make the combustion possible. Mm-hmm. And if a flammable gas vapor reacts with the catalytic material, we have the combustion process, and this creates then CO2 and water and a temperature increase. And this temperature increase will heat up the wire and change the resistance on it. And that is it.
Yes. So we're putting current through a piece of material, then we're introducing gas, and that changes the temperature, and then we measure the shift in the current.
Correct. No. We are not measuring the shift in the current. We are measuring the shift on the temperature.
Right.
Not really the temperature. What we measure is the change on resistance. So that means you have a resistance of the coil at, I would say, 400 degrees, which is then some ohms. Yeah. And when you combust a flammable gas, this will change it, so by some ohms only. Yeah. Okay. So, and the difference is what we measure. So we need a reference to compare it. And that means we need not only one Pellister, we need two, so that we have two elements which have the same resistance, same behavior, but as soon we have a combustible or combustion, one will change, and then we can see the difference, and this is a direct proportional information about the gas concentration we want to measure.
Okay, so you have a working element and then a reference element.
Correct.
And we're measuring the difference between the two.
Yes, correct.
And are the characteristics of these two elements the same, or do they differ slightly?
So yes, they differ. So the traditional way or conventional way was always that you both have a platinum wire, you have a catalytic material, and then one is coated so that it gets passive. It will not combust the flammable gases, so that you have a comparison. Yeah. Because both are arranged in a chamber. So I have a sample here with me where you can see the two pearls which are hooked on the pins, these golden pins. Mm-hmm. So they are in the same arrangement, so they will see the same environment, and if both would be active, in the end both change the temperature and would also change the resistance, and the effect is zero.
Yeah.
So that's why you need an active and a passive pearl, how we call it. So one will change, the other not. And if you arrange this in a Wheatstone's bridge, then you can measure the voltage drop over the two bridges. So this is the way how it's done conventional. Yeah. So Dräger has a patent way to make it different, because this effect or this arrangement has some negative properties or effects on the measurement performance. So when both or if both have the same material but not completely the same, if you have changes on temperature from the outside, so the effect what you have in the morning, in the evening, outside, humidity, then one will change different to the other. Yeah. So and then you will see on sensors that they drift overnight or in the morning at the 0 point. So you see some small fluctuation, and that's something you want to avoid, because this could give false readings, false alarms. User get nervous about, is something present or not? And there's a possibility by the patent principle Dräger we use instead of one active and a passive, we use two active pearls, because then the same material properties and they will change in the same way. To avoid that both change, we have them arranged in a small separation. So there's a small cap about the second pellistor. So that the gas can only hit the first pearl, and there's a small aperture connecting both, that only a small amount of gas can move there, so that we have always this security to see that the second pearl will see the gas or the ambient conditions, but the majority of the combustion will be happening on the first pearl. Yeah?
Okay, so there is the ability for the reference pearl to adjust
Correct.
The background. Okay.
Yep.
Before we go on too deep into the what can affect the sensor, let's look at it. So it measures all flammable gases. Is it important to know if there's a mixture of gas, or do you always need pure target gas? Which might not be realistic in the real world.
So when you design a gas detection system and you select, I would say, a sensor technology, and you want also to adjust or calibrate it, it's always important to know what kind of target gases you expect, or vapors, especially if there are mixtures. So if it's not pure methane, but you have, for example, a mixture of different alcohols or hydrocarbons. Because I would say on the gas it's simple, but if you come to liquids, then we don't measure, I would say, the liquid, we measure the vapor, which depends on the flash point of the substance. So, and we need a certain amount of vapor concentration so that this principle works properly. So on the one thing, as we explained in the beginning, we have in combustion and we have additional energy which is then provided, as this is direct proportionate to the chemical reaction. As soon you have hydrocarbons with longer chains, so with more C molecules inside, it gets more difficult to break them, so to cut this into CO2. So simple hydrocarbons, methane, propane, these are easy to detect, but as soon you have very long chains, then it's difficult, and then the temperature increase gets lower and lower. Yeah, so the sensor is less sensitive, and to make the sensor capable to detect it, you need to increase the amplification. So, and to find always the right balance, so what is the right amplification or what is the right setting on the sensor, you need to know which gases or vapors are present to find which is the one with the lowest signal.
Okay, so you need to know the compound. That's an interesting point you make about the vapor as well. So someone might have a liquid that they know is flammable, but it's important to know that it's actually going to create vapor that we can detect in the gaseous form.
Yeah. So, and there's also, I would say, this situation, even hydrocarbons, we can smell them because a lot of these are aromatic. So if we are talking about the vapors, but this doesn't mean that you can detect them in a good way. So our nose is very sensitive in a lot of cases, either if we are talking about sulfur compounds or also on the aromatic hydrocarbons. But these are levels of ppb or ppm. And if we are talking about flame detection or flammable, then we are talking about lower low explosion limit, and this is in the direction of volume percent. So that means it could be cases that a user or operator will smell a hydrocarbon, but it's far away to get dangerous. We have seen this in customer installation. So there was an airport where the kerosene was pumped by an underground tunnel from a tank farm to the different places where the aircrafts are stored or waiting for fueling. And this tunnel was designed in a way that also for maintenance you could walk through. So you have always some leakages on pipes. So even if they are, as soon you have a flange, you have a valve, small minor leakages can happen. And the operator went through the tunnel and could smell the kerosene. So, and they installed a gas detector, and it didn't indicate anything. To explain that, I would say that aromatic has nothing to do with lower explosion limit is sometimes difficult for the people to understand. So, but in the end, the kerosene has a flash point depending on what kind of jet fuel you have, of roughly more than 60 degrees. So it means under normal ambient condition, you will never create an explosive atmosphere. So only if you heat it up, and this is difficult to achieve.
So we're talking about flammable gas detection. Now I go back to my GCSE or high school science. So I'm assuming we need oxygen for this sensor to work?
Yeah, correct. So all combustions, or I would put that way, when we talk about explosion protection, then we have two kinds of things we need to look at. The one is, I would say, explosive mixtures and explosive atmospheres. And atmosphere always relate to oxygen. So what we normally do is explosion protection in what we call atmospheric conditions, so an atmosphere where a human being can be, so like us. And then we have normally 20.9 volume percent oxygen. So the catalytic bead principle always need at least 10 to 12 volume percent to combust the flammable gases or vapors in a good way to get a linear signal. The problem is if the concentration goes below, you don't have the direct linear indication of the concentration which is present. So it's like when you compared with cars in the old time, when you wanted to start the engine and you had a flap to adjust the oxygen concentration in the engine. So either it was too much fuel or not enough fuel. So this is something like for the process of the catalytic bead.
Do you remember those cars, Megan, where you need the choke?
I do not. I do not.
Good old times.
So these sensors are under a lot of temperature change when they're detecting gas. The passive detectors sensors, right? Like the gas has to flow over the sensor. Does this heating and cooling of temperature, does it take a toll on the sensor? Like what is the sort of life of these sensors?
Yeah, so we are talking about 400 degrees, but the changes we have are just a few degrees. So if I would say we are not using pure oxygen with hydrogen, so having a huge propagation inside, so this will not, I would say, reduce the lifetime of a catalytic bead sensor. So if you have, I would say, gases like methane, propane, this kind of sensor can last easily 10 years or longer. So what is limiting the lifetime of these technologies are always compounds which are corrosive, like chlorine or sulfur, which creates corrosion at the gas inlet and also in the combustion chamber. Or this catalytic material, which is around the coil, includes some kinds of metals. So this is a small granulated aluminium and other metals, and they will corrode. And if these corrode, the active surface, what we have for the combustions, get smaller and smaller, and the sensor get less sensitive. So this is the limiting factor of the lifetime of these sensors. And if we have other compounds like silicons, they are polymerizing, so they make a kind of coating over it, and this will not disappear.
So if a customer was thinking about using catalytic bead, but they also had an excess of chlorine in their production, would it be wise to choose this sensor, or would it be best choosing a different type?
I would say this is always, so the sensor could be used, yeah? The question is always, we call this, it's a dose, yeah? So how much chlorine the sensor will see under which conditions. So if it's, I would say, a dry condition, then you will have not a lot of corrosion effect. If you have at the same time high humidity, then you will have more easily a corrosion.
So it's site-specific.
Correct. And to figure out how good the sensor will operate is something, but I think we will speak about it as well, is adjusting the maintenance or calibration interval to figure out what is a good period to use it and when to replace it.
Yeah.
But the good thing, the sensors are very robust, this kind of technology, reliable, and it's easy to maintain, yeah?
So it's possible, but you just need to be aware of the kind of the maintenance schedule.
Correct.
Yeah.
Correct.
So I just want to summarize on the technology. So we're using catalytic bead for combustible gases. It doesn't matter if there's a mixture, but we need to be aware of it when calibrating. So we're running current through a coil of wire, and then we're looking at the combustion rate, and then the change in resistance in the coils.
Correct.
Okay? And we need oxygen as a minimum. It was 15%, something like this?
No, 10 to 12. So so when we look on the standards, so just on the physics, it's minimum 10%.
Yeah.
Our sensors from the design require 12 volume percent.
Okay. And why is it 12 volume percent? Like, why is that the level?
So we use, I would say, or in an application where you want that a combustion are not happening, you use this principle to reduce the oxygen level. So by using nitrogen, for example, when you have a pipe or you have a process where you have gas or liquids which are combustible, then you could replace the oxygen concentration. We call this inertization.
Yeah.
And by institutes, they have figured out that depending what kind of hydrocarbon or flammable substance you have, the oxygen concentration, they call it the minimum lower oxygen concentration, differs for each. So, and for methane, for example, you need to be below 10 volume percent, then you're on the safe side. Yeah. So in a process where you, for example, have pure methane and you reduce the oxygen level just to maybe 9.5 volume percent, nothing will happen because there's for the reaction not enough oxygen to create a combustion and to continue this.
Yeah. Okay. So that's a little summary on how it works. I guess we want to know the drawbacks and why you would pick these sensors over something else. So let's start with the external factors that maybe take a toll on the sensor. So like I think you mentioned earlier, like humidity and temperature and things like that.
Yeah, so I would say it's conventional. It's a well-known technology. It's very robust, as you said. But nevertheless, you could have always influences by the environment. So that nowadays we have other technologies which are less sensitive to it. And especially when we have installation, for example, you have a process, you have a duct where you want or you have to measure in the process under certain conditions where, for example, oxygen level is not high enough, temperature is too high. So parameters which limit either the lifetime or performance, then maybe the sensor is not the best. But I would say in the most of other cases, the sensor is very good because it will detect most of the hydrocarbons, and especially when we look to the change in our environment, so going to new forms of fuels like hydrogen or ammonia, then this kind of technology is perfect because hydrogen you can't detect, I would say, with other technologies on constant level. So this is the only one which on this price level, on cost level is acceptable to use. Yeah. There are other technology, high sophisticated, but it's not makes sense to use it. But also with ammonia is quite, on the one side, it's very toxic on low level, and on a higher level, it's high flammable. And ammonia will be from my point of view, the future fuel when we want to use hydrogen in Europe. Then for the transportation, most probably they will use ammonia because we have the infrastructure.
Yeah.
So a lot of ports, terminals have already the conversion technology and the installation to handle ammonia, which is completely different compared to methane or propane. So we are ready to use ammonia and convert it back in a way to hydrogen, so that we have something to replace methane on long term.
Mm-hmm.
So the hazards may be changing in the energy sector.
Yeah.
But the technology that we can use to detect that has been around for many years, right?
Yes.
So it's new hazard, but same method to
Correct.
detect it.
So for the user, it's very simple because it's the same technology, the same procedure, what they're used to. It's just a different hazard, as you said. Mm-hmm. And this doesn't mean they need to do investments or changes. Yeah.
Mm-hmm.
So what I often see is maybe a potential misunderstanding between accuracy and repeatability on spec sheets. They're often talked about and sometimes interchanged. Can you help talk about the accuracy and the response time you could typically see on a catalytic bead?
Yeah, sure. So response time. So the principle what we use, we want to combust, and that means the gas needs to reach the pearl. So based on the physics we call this as a diffusion effect. Yeah. Mm-hmm. So when we have outside a certain amount of molecules and a lag inside of the combustion chamber, then automatically the gas molecules will diffuse into the chamber and will be combusted. And then you have a continuous flow, so other molecules will follow. Mm-hmm. So this process on catalytic bead, if we are talking on hydrocarbons or on hydrogen, is a few seconds. Mm-hmm. As soon we come to the effect that these have longer chains, it takes longer. So the response time goes up because these kind of molecules are more lazy to move. Mm-hmm. Yeah. Mm-hmm. So on the response time, this kind of technology, I would say, is most appropriate to cover all the things what you have.
Mm-hmm. The speed of response relies on where you position these detectors.
Correct.
Compared to where the leak source is.
Yeah.
So when we state the response time on specification sheets, that's from the point in which the sensor is saturated.
No, or
the gas is accumulated around the sensor.
Yeah, so the testing. So we normally, one of the things is when we use gas detections, always these kinds of equipment needs to be, I would say, tested, approved by a notified body. Mm-hmm. And to make this comparable between the different test houses, they have standardized the procedure, yeah? So that not one is testing different to the other, so that you have maybe one has a few seconds, the other 10 seconds, only because of the procedure. So the standardized processes, you have a chamber, defined volume, where you position the detector inside. The sensing element is blocked by aperture, and then you flood the chamber with a defined concentration. And then you open the aperture and measure the time, how long it takes to get the expected concentration or reading on the detector of the sensor.
And that's a specific gas in that test, is it?
Correct. Yeah. So standard is always to test with methane, propane, and hydrogen. And the reason is that hydrogen you can always detect. It's very easy to ignite. Methane, so this is one of the things what you will see in the field is sensors get less sensitive and most probably to methane because the molecule structure is more difficult to break compared to propane or hydrogen. Mm-hmm. Yeah.
And why is that?
This depends on the bindings you have from the C to the H. So the methane, the C is in the center, and you have the 4 elements around. Yeah. Hydrogen is a double. It's just 2 hydrogen. So they are very easy to break apart to react with oxygen. So it's always a question what kind of bindings you have between the molecules and how strong these are. Mm-hmm. Yeah. So coming back to your question about repeatability and accuracy, so the testing with the chamber is about response time. With this, you can't figure out how reliable or repeatable the measurement is. For this, you use normally an adapter so that you can use maybe you take it, you have the gas flow in front of the sensor, and if the flow is not high enough, then still you have the principle of diffusion that the gas will diffuse in. Yeah. So, and for the accuracy, what you do is then you apply a defined known concentration and check how accurate is the reading of the sensing element. As we are talking about low explosion limit, normally there's not this high demand on being accurate on ppm level, as the unit is either 0 or 1% LEL. So behind this could be a huge concentration, So, and repeatability would mean it doesn't matter how accurate it is, but if you always hit the same point, then this is the repeatability, So, for example, if you play dart and maybe you don't hit the center, but you always hit the same point, then your repeatability is very high, but your accuracy is not good.
Okay.
And is it important to have all of them working together?
So you want to have a certain accuracy because you want to know how close are you at the low explosion limit. So in the range of the percent LEL, and in the standards you test this behavior. There are certain thresholds which you need to fulfill. On the repeatability, it's quite more important because if you want, you have a complete safety chain behind. You want that every time. So if you have 10 times an alarm, you want 10 times that the complete chain is activated. Oops.
So when you're installing, so let's look at the considerations when we're installing. So what is there anything that stands out particularly for the catalytic bead when locating a device?
I would say yes. When we compare to infrared technology, for example. So in a lot of cases, sensors should be orientated that the opening looks or is orientated downwards. So to protect, on the one hand, the opening for dirt, dust, also in winter time for any kind of snow, or if you have heavy rain, so that water drops are not blocking the gas entry. So this is more particular, I would say, on catalytic bead, but also on some others. If you have a designed sensor which is, like we described at the beginning, active-passive pearl, then you are limited in this direction. Because if you would mount it horizontal, then you would have problem. Then you have a kind of chimney effect inside, because depending where the hot pearl is, you will have a cooling effect with the airstream going by. So you have I would say, the heater will always be active, and creates a kind of reading which is not present.
So like a false zero or a drift, maybe?
Yeah, correct. Okay. And if you have, like our design with separation, then it doesn't matter.
Okay.
The only thing what you shouldn't do is pointing up, because then the probability is quite high that the entry will be blocked. Why we offer the effect to measure in this direction? When you have air ducts or pipes, you need to control. Normally they go from a bottom level to the high level for the ventilation to go over the roof away. And by this design, you can have your pipe and then the sensor sticking in so that you can measure in the pipe instead of having a separate turn so that it can stick on top of it.
So when you place it inside a duct, is there a maximum flow temperature? Is there a limit to what you can stick it into?
So from the sensor itself, high temperature is not the problem. It's more about I would say, the characteristics what you have for the explosion protection. If the temperature is higher, then the protection levels inside will not behave as expected. For this, we have special designed sensors which use a different compound inside so that you can measure up to 150 degrees. So if you have an exhaust from a combustion engine where you need to control if, for example, hydrogen is still present, so the combustion was not perfect. This is on temperature. On airspeed, the problem is if the airspeed or flow is too high, then we don't have anymore the effect of diffusion. Then it's a different effect what you influence. And then it's like the gas normally moves by, is combusted, and automatically you suck in new gas. If the airspeed is higher, you press more gas in, you combust more, so you get a higher reading. So instead of, for example, 50% LEL, you suddenly get 60%, just by the physical effect that more gas is available to combust. So it's on looking from the safe side, it's safe, because you get always a warning.
Too high.
Too high is always better compared to too low. So, but that's something you will find in the spec sheet of a sensor, indicating what is the impact of airspeed or flow. So normally what you measure is up to 6 meters per second. Yeah,
Okay.
and depending on what is the diameter, this defines then the airspeed. If you have ducts which are, I would say, half a meter, 1 meter, and you have higher airspeed, normally you make a side pass so that you have a chance to define the speed of the probe you want to measure.
Okay.
And what do engineers need to take into consideration about the calibration of the sensors? Is there a standard time interval that needs done? Is it every 6 months, every year? Or is it a little bit more specific depending on what the site needs?
Yeah, so this is unfortunately, I would say, always it depends on. So it could be from 3 months up to 12 months. So for example, if you want to measure hydrogen, the sensor is very sensitive to hydrogen. So it will be very stable over more than 12 months. So just installing in a, I would say, clean atmosphere, there's no need to test it earlier. If you have application, you're in a kind of industry where a lot of dirt is around, then we have always the risk that dust or other things could block the entry. Yeah, so it means we need to know how clean is the atmosphere. If we want to detect solvents, then we know that these give a low reading, so the sensor is less sensitive. So that means it could be that the sensor gets earlier insensitive or not sensitive enough. So it means in certain application, maybe you need to calibrate or check the sensor every 3 months. So it really, I would say, it depends on what is the target gas you want to measure and what is the environmental condition. If this is not, I would say, if you have no experience, then you have to work out the interval. So by starting, you calibrate the sensor, and after 2 weeks or 4 weeks, you check. And if the deviation is less of 10%, you double. And then
you can kind of build it up.
Yes, correct.
So it's very difficult to make specific claims on the calibration frequency without knowing the site. So
correct.
So the stated calibration frequency is always a guide, right? So you should know that's what I take away from that.
Correct.
Very good. So what we like to do when we wrap up is take kind of 3 takeaways that the viewers can stick in their mind. So the first one is when is the catalytic bead the correct choice?
I would say every time when we speak about flammable gases and vapors, which a flash point below 50 degree, then it's always good.
Yeah.
Especially if you talk about hydrogen or ammonia.
Yeah.
So that's a very good choice.
Okay, good.
And what's the biggest limitation or misconception that people often have about the sensor?
This is something or the example I mentioned with the airport. So, so understand that the smell of an hydrocarbon doesn't mean that it's at this point on a flammable level or on a level that it's detectable by combustion. Yeah.
Okay.
And regards to maintenance, what's the most important thing about maintenance for the catalytic bead?
I would say if we calibrate the sensor, or it's, I would say, valid for all kind of sensor technologies. Calibration should always be done under the condition of the operation, because temperature, humidity have always a physical effect on the sensor, especially on the 0 point. If you calibrate, I would say, on a level which is where we have very dry condition, and afterwards all the time you have 60 or 80% relative humidity, you will see a drift in the 0 point, either positive or negative. And this could trip a warning. So it's always important, first of all, condition of calibration. Second is looking what is the calibration gas. The best is always take the target gas. Some are difficult to handle. Then you must be sure that the gas what you take is, I would say, you use the right factors, so that your accuracy don't get lost, so that the sensor is not too sensitive or not sensitive enough.
Okay, so it's around the target gas.
Correct.
Is important. Excellent. Well, thank you, Marcus.
Yeah, thanks, Marcus.
So that's a wrap for Beyond Tech podcast. If you're working on any projects which you need more in-depth knowledge around sensors when you're specifying it, you can go to our website, Dräger.com/EPC for more information.
Yeah, and again, thank you, Marcus, for joining us. If you found it useful or beneficial, be sure to let us know in future if there's any further topics you'd like more information on.
Next episode, we'll cover another technology, but the rules are the same. So no products, no fluff, and we look at real-world applications.
Yeah, thank you.
Thank you.
Thank you.